So this is open loop operation. Output so it can't only be regulated, but there is no feedback, so it will not respond to your transient also. Okay, so your transient will mostly depend on your output capacitor you have. So let us say VDD equal to 10 volt and this is your DC to DC. V out equal to 1 volt. Okay. So what you can do, switch cap 1/2 X. So this is 10 volt, this is 5 volt. Now, so when I say DC to DC, you say this is inductive actually. So in this case, duty cycle is D min, okay, or closer to D min. This is your V out. So another example could be your VDD is .5 volt. This is your DC to DC converter and you require 3.3 volt output. So this will be your obviously boost, correct, and this is buck, this is also buck. So I will split it into, so VDD equal to 2.5 volt, I will pass it to 2x switch capacitor DC DC. So you will get 5 volt. Now use a buck. So and this, if you do let us say a combination of this 2x switch cap DC DC in this case and buck, so one advantage is it will respond to transient much faster because it does not have any right half plane 0, there is no discontinuity as such. Another advantage is your output ripple, there is no discontinuity. In case of buck, when your output is disconnected or while inductor, sorry, in case of boost, while inductor is charging, output is disconnected. So output capacitor is supplying all the current. So in order to get the same ripple, your output capacitor requirement will be much large compared to buck. In case of buck, we know the inductor current is continuous. So the capacitor size will be much smaller in case of combination of switch cap and DC DC converter. Another advantage is we know the inductor current is boosted by 1/1 minus D. In case of buck, it remains same as load current. correct. So, your I square R losses are lesser compared to that, so efficiency will also improve. So, this will have better transient response because no right half plane 0. Okay. Second advantage is smaller output capacitor or smaller ripple with same cap. Okay. So, let us say you are putting 50 microfarad in boost. So, in the other case, if you put up 50 microfarad, you will see ripple smaller than compared to the other case. Improved efficiency because IL equal to I load. Okay, this is case of buck. Here IL equal to 1 over 1 minus D into I load. This is the case of your boost. Okay. So, based on the requirement you can choose. So, now if I want, let us say application is something different and I want to regulate the output at 1.5x with using 2x DC-DC converter. So, this is my, I will just copy this. Okay. So, this is your clock generator, and clock generator is nothing but non-overlap clock generator. So, it will get any clock input and generate phi and phi bar. Okay. And you can say it has enable signal also. So, when enable equal to 0, phi equal to 0 and phi bar equal to 0. Basically, all the switches are open. So, now if I have a comparator minus plus VREF okay. So, my V out required here, let us say 1.5 times of VDD, which means VREF is 1.5 times of VDD. Okay. Or let us take some numbers, it will be better. VDD equal to let us take the same case 2.5 volt and V out is 3.3 volt. So, Vref is, so if you are using a feedback resistor, then you can choose Vref based on that. So, since we cannot generate 3.3 volt from band gap, so let me put here R1, R2, this is your VFB, this is your Vref. So, let us say Vref is 1.2 volt. Tell me the ratio required for this. So, Vref over V out is 1.2 over 3.3. This is your beta. Okay. So, you can choose R1 R2 ratio based on this. So, what do I need to do with this output of this comparator? What do I need to control? So, what it will do? It will go here and control your enable. And this is hysteretic comparator. So, now define a window. If it goes above that, it will start switching and it will transfer the charge to output. Okay, if it is below that, so remember the hysteretic converter. So, let us say, so now what it will do actually, if this is my so my output required is 3.3 volt. So, VFB should be settled to 1.2 volt based on the ratio we have chosen. So, 1.2 volt minus, let us say, delta VH by 2 and 1.2 volt plus, okay. This is your VFB. Your average output will be here, oh sorry, the feedback voltage. So, what it will do? It will charge and then stop. When stop, who will discharge the output? Load. So, it will do like this, then again. So, what is enable equal to 1, enable equal to 0. So, it will keep regulating within that window and average output you will get roughly 3.3 volt. That is how you regulate. But if I do not force in regulation, where will output settle? Let us say losses are negligible. So, this is your I load. So, let us say we are operating at very light load. So, if I do not, where will output settle? 2x, 5 volt, but I want 3.3 volt, which means I am never operating in steady state. So, what would happen in that case? In terms of losses, if you never allow your circuit to settle to a steady state, losses will be high or less? It will be high, because initially you are charging the capacitor. In the steady state, when the output is settled, okay, let us say you have no load, then no charge transfer is happening. So, basically if you look at the total current in the path will be 0, which the current drawn from VDD to output, in a steady state will be 0 under no load condition. Okay. But under no load condition, if it never goes to the steady state voltage, that means you are still charging the output cap. So, there is a current in the path and it will always incur I square R losses. So, you can imagine like this, in a steady state ideal condition your output should go to 5 volt, but you are forcing to remain at 3.3 volt. So, rest voltage is nothing but lost in the path. So, this is just like an LDO. So, efficiency will be similar to LDO here. In the other case, if you allow it to go to 5 volt, your efficiency may be more than 90%, 95%, much higher. But in this case, basically you are throttling the output, okay, never allowing to settle, and extra voltage will be, and that is how you regulate. There is no other option here to regulate, because it is not inductive, it has a fixed ratio. You cannot control basically your output with a duty cycle or anything here, it will give you only discrete option. So, this is the only way to regulate. So, at the cost of efficiency you can regulate the output. Okay. So, your efficiency will get better and better when your regulated output is closer to 2 times of VDD. Okay. So, if you look at the efficiency curve, so your V out is 3.3 volt, VDD is 2.5 volt in open loop, V out is, so this is your closed loop, 5 volt for VDD equal to 2.5 volt. So, this is efficient, this case is inefficient as 5 volt minus let me okay, 5 volt minus 3.3 which is equal to how much? 1.7 volt. Okay. So, this is more like an LDO. Okay. So, but if you look at a under light load condition, so with this hysteretic converter, you know output is discharging with, so switching losses will automatically scale with your load, because this frequency will start reducing. So, you charge and then you wait until your load discharges. So, as your capacitor is same, your load is getting reduced. So, what will happen? Your discharge rate will be slower. So, next time you will be switching. So, it is more like a burst kind of operation. So, we call it burst mode also. So, it will send the next burst of pulses after very long time. So, which means you are switching very less frequently. So, your switching losses will scale down automatically with the load current here in this case, because it is more like a PFM operation. Okay. So, you can say similar to PFM inductive. So, which means if I want to plot efficiency curve, so let us say this is VDD. So, minimum VDD is 2.5 volt, not 2.5 volt. For 3.3 volt divided by 2, how much is 1.15? Okay. So, let us say 1.2 volt, and on higher side you go to 2.5 volt. So, where will be the maximum efficiency? Huh? What? It is a 2x, huh? 2.5 is 5 volt, 1.2 is no 3 volt output. This is 1.2 volt is not correct, huh? How much is 1.65? Okay. So, 1.65 into 2 is 3.3. So, you will get very high efficiency here, and it will keep dropping. And further, if you increase your Vin, it will. So, you may have a, let us say 90% here. So, 3.3 over 5, how much is that? 66% roughly, you might say. So, I will say roughly other, including other losses, you may get only 60% here. So, what do I need to do if I further want to improve the efficiency? So, I am always operating at 2x, but at 2.5 volt I need only 1.5x roughly. So, what I will do, I will have a charge pump which has both 2x setting and 1.5x setting. So, when it is at the lower side, your VDD operating in 2x mode, and when it is basically at the higher side operating in 1.5x. So, your efficiency will, okay. So, let us say 2.5, let us say I have a 1.5x charge pump, your efficiency will again go back to 90%. In between it will start dropping unless you, until you change the, your setting actually, the gain ratio. But now you are looking at a basically just you can say you have slicing this efficiency curve in multiple pieces, and each piece will have its peak at 90%, and in between it will be dropping. So, average efficiency will still look much better, maybe 80% or so. Okay. So, which means if you are using a only fixed ratio, then obviously depending upon if you are operating a wide range of VDD, your efficiency may not be that good, but you will get a very good efficiency if your V in and V out is fixed, and you know it is always operating close to 2x. But if it is a variable input or output, then one gain setting is not enough. You need to have a charge pump which can be configured in 1.5x, 2x, 2.5x, something like that, 3 or 4 settings, and you can improve the efficiency. Okay.